Okay, so grid multiplication. Let's go to grade 2 and grade 3. We've got rectangular arrays. I think, well, even if you weren't taught multiplication this way, you can understand what's going on here. The idea is that area and multiplication are parallel things. They metaphorically map onto each other. We use multiplication to calculate area, and we can depict multiplication with area. So here we have an area of, it is 3 by 2, or 6 units squared. And so we can talk about that multiplication fact. Although I hesitate to use the word fact, because for me, multiplication is a process rather than a series of facts. And if I'm good at the processes, that's where I will be able to get correct facts and be able to build stronger and more complex multiplication on top of simple multiplication. So then we're going to flash forward to grade 4, where the world got a little more complex and we had to do 2 digits by 2 digits. And the one I've chosen here is 13 by 12. You might have used base 10 blocks for this. I don't have a set with me right now, but I think you can imagine them. They're yellow. And you might have used grid paper. I don't have any on my whiteboard, but here's what I'm showing you. I've drawn the squares necessary to be able to count the squares in a 13 by 12 grid. And then, because I wanted to count them more easily, I drew those black lines and made quadrants. So you can see that I've created a 100 square and 3 rods, if you will, of 10 here, 2 rods of 20 here, and 6 in the corner. That can then transfer if I want to think a bit more symbolically and do without the graph paper. I don't tend to do without it very quickly when I'm teaching, even with my own children. And I distill this, so I'm no longer drawing all the squares. I simply say 100, or 30, 20, 6, which I can see sums to 156. Or if I want to get even more symbolic, I don't even think about the shape. I just know that the 10 will distribute down through the 12. The 3 will distribute down through the 12, and likewise horizontally. I call this a symbolic representation. And you can see that it maps very nicely onto the grid representation, which also depicts the distributive property. The 10 distributes down through the 12. The 3 distributes down through the 12, and likewise horizontally. Okay, so we then get our product, which is 13 times 12 is 156. The other nice piece that's transparent here is the commutative property. Here I could reverse the 12 and the 13. I would still have 156 if you know that from your own study of properties. But we can also demonstrate it with the above artifacts. We can take that grid rectangle and reflect it such that the 10 plus 3 is down the vertical side and that 12 is the horizontal dimension. Nothing changes in the shape or the size of that rectangle. It simply changes its orientation. The same things will happen in those 2 more symbolic representations below. The 30 and the 20 switch places is all that will happen. And that's a nice thing for kids to see, the distributive property and the commutative property working in a way that they can understand why and how those things are true. This leads me to junior high, grade 9 here in Alberta, and a question asking us to multiply x plus 3 times x plus 2. Now, often I think teachers resist this work, the work with algebra tiles, because they have often done other kinds of work first, where they've taught algorithms to get these products. But as you can see by the previous learning that these children have done in their elementary school, if we move directly here and we teach the multiplication through the algebra tiles, I don't think kids do resist the algebra tile work when that is done. So here what I've done is try to mimic what we've just done on the other part of the board. This is my x plus 3 dimension. This is my x plus 2 dimension. When I multiply the 2, I get an x squared. I get 3 rods of x, 2 rods of x down in, horizontally, and there's the 6. I would really like to be showing this to you with concrete images as well, and I perhaps will create another video where I can show you those ones. Then if we take that same idea and go more symbolically, we can create the very same dimensions and the same products, but talking about them symbolically. Again, the distributive property is clear, and the commutative property as well. And then we get our product, the 2x and 5x add up. The 2x and 3x add up to 5x. Now, I want to look back because if it's interesting to you, you might think about that as a function if you're watching this with higher level mathematics. X squared plus 5x plus 6 as a function where this is one of the points actually. So this is where x is 10 and you get 156 as your output. What would happen if x were 5? Well, this square would be 5 squared or 25. These would be rods of 5. Another 25 and another 6, so you'd have 56. And then you'd be able to see that too in the way 5 subs in to these values, or 10 subs into the values, or whatever you want to try. So you can connect this to patterns and to functions. So here's an example I want to do in live for you actually, so that you see how this might work. So I need to draw 2 x's and 1. Again, it doesn't matter whether I go horizontally or vertically with my first dimension. And there's my x plus 3. Good. So now I need to fill in. I need an x squared, filling in that space and this space. By the way, I actually teach factoring before I teach multiplication when it's algebra. And I fill in where I need x's. I'm going to need a number of them here. And another column, because that 1 distributes onto all 3 of the units, the 1x. The other x distributes to all 3 of the unit squares. And then the 1 distributes onto the 3 unit squares. So I know my product already. I'm going to draw this or talk about it symbolically. There's my pictorial. So here is 2x plus 1 and x plus 3. I get 2x squared, multiplying x, 6x, the 2 columns of 3x we saw earlier. And here we have the grid complete. So I know that the product will be 2x squared plus 7x plus 3. So there. It may feel like it takes time, and it does in those first few examples, but very quickly students decide what they want to do to make shortcuts. And I certainly don't do this any longer, but that doesn't mean it's not a necessary step to pause in until these ideas take hold and the connections get made to these earlier examples in a student's history. So I do work on this, and then I move here, and I still do all of my multiplication in this space. Sometimes I don't have to write these factors in. I can just eye them up in my mind, and I go here. But it's certainly something to rely on. I think the one mistake teachers make is when things get easier for them and they refine their own algorithm, they try to share those shortcuts with students, where in fact it's the building of the shortcuts that reflected what the learning that went on in our own minds. Thanks for watching.